In this video, we are going to use our new tool, the implicit function theorem, to justify one of the definitions that we had given, the definition of the tangent space to a hypersurface. Recall that a hypersurface was nothing but a level set of a C1 smooth function such that the gradient of that function does not vanish at any point on the level set. We had also defined the tangent space to be the collection of all velocity vectors of curves that lie entirely in that hypersurface. The only issue is that it's not even obvious that there is one curve that lies entirely in the hypersurface other than a constant curve, of course. So now we are going to fix these issues and make everything rigorous. I will prove a slightly more general lemma that does the job for us. Lemma. Let f from u to r be a ck smooth function. Suppose for some point A in this open set U, we have f of A is equal to 0 and the gradient of f at A is not 0. Okay. Let V in Rn be such that the inner product V comma gradient of f at A is 0. In other words, this vector V is normal to the gradient of f of A. Recall that the gradient of f of A was supposed to be the normal to the hypersurface. So this vector V is normal to the normal. In other words, V is supposed to be a vector in the tangent space. Let S by definition be the set of all points U, set of all points x in U such that f of x equal to 0. Note, in this slightly more general setting, S need not be a level hypersurface. I'm just requiring that the gradient of f at A not vanish. So essentially I'm taking the condition in the definition of hypersurface and focusing my attention near a point A. So that's why I said this lemma is slightly more general than what we need to prove. But since this is a local thing, existence of a normal and existence of a tangent hyperplane, they are all sort of local notions. It's better to prove it in this setting to have clear understanding as to what is relevant and what is not relevant. Okay, so this is the setup as follows. We have this function f. We are considering the level set of this function, which need not be a hypersurface, but at least at the point A, the normal is well defined. The conclusion is as follows. Then we can find a ck smooth curve gamma from -1 to S such that gamma of 0 is equal to A and gamma prime at 0 is the vector V. Okay. So what this shows is that given any vector that is normal to the normal, then we can find a curve that passes through this hypersurface, that in fact lies entirely in this hypersurface, such that the velocity vector of this curve is nothing but the pre-specified vector V. Okay, so we have a second part to this conclusion. In particular, the set TAS, which is exactly defined as in the case of hypersurfaces, the set TAF such that V such that there exists gamma from -1 to S, not Rn, S such that gamma of 0 equal to A, gamma prime of 0 equal to V is the orthogonal complement of the space spanned by gradient of f at a. Okay, so we have got several conclusions. One is that any vector that is normal to the normal will be a velocity vector of a curve passing through the surface, and using that we will show that the collection of all such velocity vectors is exactly the orthogonal complement of the space spanned by gradient of f of a. Okay, so one of the reasons why I wanted to prove this rather than just directly moving on to the theory of manifolds, where we will study the tangent space again in more general situation, is that this particular lemma, though very simple and straightforward, illustrates the implicit function theorem rather visually. And if you understand this lemma, what is about to follow, the general notion of manifolds and the notion of tangent space in general, will become quite easy. Okay, so since the gradient is not zero, we can assume without loss of generality, that the nth derivative dn of f at a is not zero. This essentially just means renumber the coordinates so that the last number in the gradient is not zero. We can always do this. Write this point a as a prime comma an, where of course an is a real number and a prime is in Rn minus 1. Okay. Now, because the nth derivative is not zero, the implicit function theorem immediately gives us the implicit function theorem guarantees that we can find open sets V subset of Rn minus 1 containing the point A prime, and an open set W in R containing an and a CK smooth map. That is essentially going to say that this piece of the hypersurface, actually it's not really a hypersurface, this piece of S near A is going to be a graph. So we can find a CK smooth function phi, let's say from V to W, such that S intersection V cross W, that's just the portion of S in this product neighborhood, is going to be nothing but the graph x comma phi of x, such that x comes from U. Okay, so this immediately follows from the implicit function theorem. We also have phi of A prime is an. Okay, so what we have essentially done is that we have expressed a portion of S near this point A as the graph of a CK smooth function. Okay, and another interpretation is phi, this function phi is sort of parameterizing the surface S near the point A. Okay, now what we are going to do is define this graph map, essentially G from V to S by G of x is nothing but x comma phi of x. Okay, now what we are going to show is TAS, so rather I can write this as a claim. What we have defined as TAS is nothing but dg at the point A, or rather, yeah, dg at the point A prime of Rn minus 1. Okay, this dg of A prime is supposed to be the derivative of this map G, and we are going to claim that the tangent space TAS that we have defined is nothing but the image of this map at the point A prime, the entire image. Okay, so to prove this, first observe that rank of this dga prime is obviously n minus 1. It's obviously n minus 1. It's a full rank matrix simply because the first coordinate is just g of x equal to x comma phi of x. So this will be immediate by looking at the matrix of this map dga prime. From that it will be really clear. Okay. Now, because the rank is n minus 1, the image that we are interested in, the image dga prime of Rn minus 1 is a n minus 1 dimensional vector subspace of Rn. Excellent. So we are getting somewhere. We have got that this vector subspace is going to be n minus 1 dimensional. Okay. Now, what we have to show is that this vector subspace is nothing but TAS. That's the ultimate goal. So call this vector subspace capital lambda. Let's call this vector subspace capital lambda. What I'm going to show is that if W is a vector in this lambda and V in Rn minus 1 is such that dga prime V equal to W, then I'm going to manufacture a curve that goes through the surface S and has velocity vector at 0 exactly this vector W. How am I going to do that? Then consider the curve gamma from minus epsilon to S defined by T, as you can guess, maps to G of A plus TV. Okay, so what I've essentially done is I know that this map G parameterizes S near this point A. I know that dg A prime of V equal to W. So what I'm just going to do is I'm just going to consider the curve that is in the direction V. There's just a straight line in the direction V lying in the domain V. And then I'm just going to act G on that, and this will make it into a curve that lies in the surface S. And of course, because of the way things have been defined, one second, there's a slight error here. This should be A prime. Because of the fact that G of A prime is nothing but A prime comma AN, which is nothing but A, this curve does indeed pass through the point A, and the way things have been set up, the derivative will be immediately be seen to A. Okay. Now this epsilon is so small, where epsilon is so small that A prime plus TV is entirely in this neighborhood V, in this open set V. Okay. T coming from minus epsilon. Okay. Now in the definition of the tangent space I had given, for concreteness sake, I had restricted myself only to curves whose domain is the specific domain minus 1, 1. Now this curve's domain is certainly not minus 1, 1 unless this set V happens to be somewhat big. it's just minus epsilon epsilon. So I'm going to leave it as an exercise for you. Exercise. So extend gamma to a CK smooth curve defined on minus 1 1. Defined on minus 1 1. Okay, so what is happening is this curve gamma now is just defined on minus epsilon epsilon. This is actually irrelevant actually, what the domain of this curve is, as long as gamma of 0 is equal to this point A. It really doesn't matter what the domains of the curves are. I'm asking you to make that precise. Okay, show that gamma can be made into a CK smooth curve defined on minus 1 1. So you have gamma which is defined on a portion. You have gamma which is now defined on a portion. This is going to, so let's say this is this surface. You have the image of this. What I'm saying is you can define it, you can extend it to minus 1 1 also, minus 1 1, in such a way that the curve continues to be a smooth curve. Okay, so this is a somewhat little bit of thinking needs to be done to solve this, but it's a very interesting exercise for you to grapple with. Okay, so we have extended this curve to a curve on minus 1 1. Now by the chain rule, gamma prime of 0 is nothing but this vector w that we wanted. Okay, now this, what we have essentially shown from this consideration is the fact that this vector space lambda that we have, remember that was the image of DGA. We picked W from that image. So this looks like a capital W. So let me just make it small w. Okay, so we picked this vector W from this lambda, and what we have shown is that there is a velocity, there is a curve whose velocity vector is exactly W. So that means that this lambda, capital lambda, is nothing but a subset of TAS. Okay, now the claim is that lambda is actually equal to TAS, which will prove that TA is also n-1 dimensional. But we have earlier shown that TAS is a subset of this span of gradient of f at A orthocomplement. Okay, we have already shown this. Of course, there we showed it for a hypersurface, but the proof is entirely local. It really doesn't use the fact that S is globally a hypersurface. Only the behavior of the normal at the point A really matters for that proof. Okay, putting all this together, we have this chain. Lambda is subset of TAS is subset of, I'll just be a little bit loose with notation and just call this orthocomplement, gradient of f of A complement. So we have this chain, and immediately we see that this is an n-1 dimensional subspace. So this is n-1 dimension, this is n-1 dimension, because it's the complement of a vector in Rn. So that means all three have to be equal. So hence we have equality above. We have equality in the above chain. Okay, so this concludes the proof that the tangent space is going to be n-1 dimensional. It's also going to be exactly the complement of the normal, and it's also going to be the image of this derivative of this graph mapping. So this is an excellent starting point for the theory of manifolds, which we are going to begin in full earnest pretty soon. Okay, so our picture of what a hypersurface is now complete. A hypersurface, a level hypersurface, is nothing but the level set of a function that has a well-defined normal at every point, so a non-zero normal at all points, and now it has a well-defined n-1 dimensional tangent space that is also obtained as the velocity vectors of curves passing through the points of the surface. So our intuitive picture of a hypersurface is now complete. We have now made the definition of hypersurface coincide with our intuition correctly. So this lemma, as I keep repeating, is very important. So please understand it thoroughly. Much of what follows soon will become very easy if you understand this lemma. This is a course on real analysis, and you have just watched the video on tangent space to a hypersurface.